All right, I think we'll get started. So today is review day for exam 3, which is on Wednesday. If you can't take the exam on Wednesday, if you have an excused absence, let me know ahead of time. I'm happy to work that out with you. But if you don't take the exam on Wednesday and don't tell me, we're going to have to talk about that. So just give me plenty of heads up time and we can work something out. No problem. We have office hours today. Sorry, I can't do a full hour because I have another meeting across campus, but 3 to 3:45 today if you want a quick check-in. Or I made some office hours in the evening because some of you have said I can't make it during the day necessarily. So because this is a special occasion for the exam, I'm happy to do some office hours in the evening. And so these are the office hours today and tomorrow, or by appointment, email, etc. Some of you, ask really clear questions on email. They're easy to answer, clarification. That's not a big deal. Send me an email through Canvas because there's no guarantee I'm going to see it if you send it to my regular email. And again, no office hours or question answered on Wednesday because the exam will be open for most of the day on Wednesday. And so just make sure you're in a good spot to take the exam, upload your written section. Some of you have had, 1 or 2 issues uploading the written section. The best thing to do is upload it, wait 5 minutes, go back, check it, make sure it's submitted, all of that stuff. And so, every once in a while, Canvas doesn't know what it's doing. You're not penalized, if it's 5 minutes late or something like that. That's not a big deal. Although taking the exam at the last minute is not good. But anyway, just make sure the written part is uploaded and you can double check it. It only takes a few minutes. Office hours are always at the Zoom link, etc. Any questions, issues, things you want to chat about? All right, format for the exam is exactly the same as always. There's a practice exam on Canvas for you. Homework answers number 6 are up. I think the PLAs are still open. If a PLA is closed, just let me know. Sometimes I don't see that. And so all the study material should be up, including the equation sheet. Now the equation sheet's getting big because we're just adding to it. So I think there's 2 pages to the equation sheet. Maybe there's maybe that's in the next exam, but make sure you have the equation sheet ready and you know how to use it. Here are the topics that we talked about yesterday. So you can, or on Friday. So if you missed Friday's class, you can get some of the things that we covered, but we've covered a lot of ground and I'm gonna back up a little bit and make sure that we're good on diene polymerization and tacticity and stereochemistry. So those were a long time ago, like before spring break ago. And so make sure that you review those things. Along with coordination polymerization, we did a lot on ring opening polymerization. So make sure you remember that stuff. And then a lot on copolymerization and conformation recently. Any questions or comments? All right, quiet group. So I covered a lot of these slides or a lot of these beginning slides last time. I just want to remind you about what coordination polymerization is and why it controls stereochemistry. And it's the only polymerization that we cover in this class that can control the stereochemistry or the tacticity of a polymer. So you don't need to know the mechanism. You don't need to know who Carl Ziegler and Julio Nata are, but coordination polymerization, when you see tacticity in making polymers that are syndiotactic or isotactic, remember coordination polymerization. What type of polymer does free radical polymerization make? What type of tacticity? If I just do free radical polymerization of propylene, what tacticity am I likely going to get? Atactic, right? If I'm not controlling tacticity with coordination polymerization, isotactic or syndiotactic, our only choice is, since polypropylene, this is polypropylene, you know that the monomer is this, right? And there's 4 different substituents on this carbon. So this carbon is chiral, right? We've got 1, 2, 3, 4, because the chain is part of, each way on the chain is part of the different substituent count. And so if I do coordination polymerization of polypropylene, I can get isotactic or syndiotactic, depending on the details of the catalyst. But if I do free radical polymerization, which there's no control of tacticity in that polymerization, there's still chiral carbons in this polymer, but I'm going to get atactic because free radical polymerization doesn't have any control of the stereochemistry. Questions on that? All right. And the other thing that we talked about is diene polymerization. And I think this is where we ended up last time. And remember, dienes are special because there's 2 double bonds, but those double bonds are conjugated in dienes, which means you have 1, 2, and 3, 4, and 1, 4 addition. So I suggest that you review this and you know the difference between something like this. This is a diene. It's got 2 enes on each end or 2 double bonds on each end, but the degree of functionalization is 4 because those double bonds act independently. They're not conjugated. Dienes have 4 carbons in the main monomer unit with any sort of substituents. And so we went through the clicker question last time. If we do cis 1,4 addition, there's a lot of information in cis 1,4. So we need to look at something that's cis. Okay, we got that. We need to number the carbons correctly. 1, 2, 3, 4. Great. So we've only got 1, 2, 3 carbons in the repeat unit of C. 1, 2, 3 carbons in the repeat unit of D. So those are both out. And the question is the right answer A or B for cis 1,4 addition? Now, just because we call it cis 1,4 addition doesn't mean that the monomer is exactly one way or the other way, right? And so we keep the substituent on the lowest carbon. And so we just need to find a structure that's going to look like, so here's our monomer right there. And remember, when we do 1,4 addition, that means we're going to connect the 1 and 4 carbon to the polymer chain. So there's 1, there's 1, there's carbon number 2. And let's see, the substituent is on 2. So I've got 1, 2, 3, 4. Remember, when we do diene 1,4 addition, we have an electron going that way, electron coming in the center bond, 1 electron back in the center bond, and 1 here. So we're connecting at 1 and 4, and the substituent is on the 2 carbon. This substituent is either on the 1 or the 4, and so this can't be the right answer because the substituent is in the wrong place. Yes?
So you said the substituent goes to the lowest carbon. What do you mean the lowest carbon?
Oh, sorry, the lowest number carbon. So remember, from organic chemistry, you number the carbons in the ring, or you number the carbons in the alkane. And so if we've got 4 carbons in the main structure right here, the substituent goes on the lowest number. And that's a rule that you remember from organic chemistry nomenclature. Is everyone clear on this? And of course, this is in cis configuration, not trans. So make sure you know all the different dienes, 1,2 addition, 3,4 addition, cis 1,4, and trans 1,4. And of course, you only have cis and trans addition when you have residual double bonds in the monomer where you lock in that rotation, right? You don't have cis 1,2 or trans 3,4 because the double bonds are out on the substituent. You don't care about that. Any other questions? Any other comments on this? All right, this was a long time ago, so this is worth a little bit of your time in the next couple days to get sorted out. All right, you have to remember anionic or cationic or radical ring opening polymerization. This is still chain growth. And so you should remember the features of cationic ring opening polymerization versus the features of anionic ring opening polymerization. They're slightly different, right? Anionic has more living character. There's less chain transfer, better control of molecular weight for anionic polymerization. And in cationic polymerization, you have ring chain equilibrium. You have termination. How does cationic ring opening polymerization terminate? What's that called? Oh, I just heard it. Say it louder. Oh, maybe I didn't hear. Go ahead.
It's the rearrangement.
What do we, the rearrangement of what?
The ion pair.
Ion pair rearrangement is the termination mechanism for all types of cationic polymerization. So you have to go back in your exam 2 memory bank a little bit and remember what that is, but it's still a cationic polymerization. So there's also the feature of ring chain equilibrium because there's chain transfer back to the polymer in cationic polymerization. So you need to remember that. Where anionic polymerization, generally, there's no formal termination. It has living character, control of molecular weight, etc. So everything that you learned in exam 2 about anionic and cationic works for ring opening polymerization as well. Questions? All right, you can get out your clickers. I think we're on CD. Let me see. AA, that is so weird. You could try AA, but I think that this thing is CD as we investigated. Okay, people are ringing in, so we'll see what happens when I look at the grades. I'll remember that. Which monomer has the highest ring strain? Oh, I don't know why that thing's on there. Good. Looks like there's a couple more of you out there than 47. Oh, there we go. I thought so. Great. And so the highest ring strain is the lowest number of carbons. And so the 3-membered ring is going to have the highest ring strain. What do we call this group? That's called an epoxide ring, right? So when you buy epoxy from the hardware store, there's some of that type of functional group in there. It's usually connected to an R group and some other stuff like that. So what polymer is made from that monomer? So this monomer is also called ethylene oxide. What polymer do we make from this if we ring open polymerize that monomer?
Polyethylene oxide.
We make polyethylene oxide. What does it look like? What type of polymer is it, first of all? What functional group is in the backbone? How do we classify it? Yeah.
Polyether.
Polyether, right? We can see that from the monomer because ring opening polymerization, since it's not a condensation polymerization, you see the functional group in the monomer. So it's going to make a polyether. And you're right, we make polyethylene oxide, which means we have to have the ether in there. And we've got 1, 2 carbons, 1, 2 carbons. We've got everything. Very simple polymer, right? PEO, polyethylene oxide. Oh, great. Let me stop this. Of course, we make polyethers with the other 2 as well. So those things make polyethers because the ether is in the ring. And so we can identify right away what the polymer is from the monomer that we're going to ring open. All right, and you remember ring string. All right, next question. Sounds like everyone can click in because I'm getting counts. Which characteristics are true of anionic ring opening polymerization? Anionic ring opening. Electron withdrawing groups are favorable. Does that work for anionic polymerization? Stabilize that negative charge. Yep, that one sounds like a pretty good answer. Let's not stop there. Let's read all the answers and either rule them in or rule them out. There's no inherent termination mechanism. Does that sound good for anionic? Yep, we just talked about that. Ring chain equilibrium exists? No. Where does ring chain equilibrium exist? What type of mechanism? Cationic. And these are the collection questions. And so it looks like A and B are true. A, B, and C are not true. So again, the strategy for taking multiple choice exams is make sure you read all the possible answers and rule them in or rule them out. Just don't jump at the first one that looks good to you. Make sure that you get everything. Is there a hand? Yes.
What do you mean by ring chain equilibrium?
Yeah, so if you go back, I'm not going to go back in the slides now because it's going to take me forever to find it. But if you go back in ring opening polymerization, one of the features of cationic polymerization is it does backbite. So the active chain end, which is a cation, backbites on the polymer and spits out a ring. And so we just had one slide on it. It's just a feature of cationic. That's why the molecular weight control isn't as good for anionic. So you should have that vocab word with you. Yeah. Chances of you having to draw that are pretty low, but you want to make sure that you know something about backbiting or about transferring the active center back. What type of chain transfer is that? This ring chain equilibrium. What might we call that? If we're transferring the active center back on the same molecule. Intramolecular, that's right. Intra, within the same molecule, not inter. Good. All right. Good. We got the right one. That's nice. All right. Next clicker question. Up to 57. This is looking pretty good. Bless you. Which monomer would you choose to make the polymer shown below? This is an important question because this really shows me that you're able to figure out what's going on with ring opening polymerization. So what type of polymer is this to start off with? How would we classify this polymer? Polyether, polyolefin, polystyrene, what is this? Ester, great. And it's a polyester because you know that this side of the repeat unit is connected to the other side of the repeat unit. And every time you have an oxygen and a carbonyl next to each other and no oxygen on the other side, as in polycarbonate, this is a polyester. Okay, so we need to look for the ester-based monomers. And so which monomer is not an ester? There's only one of them up there. E. E is not an ester because there's a carbon in there. Otherwise, we've got a lot of polymers to choose from. And so how are we going to do it? So you can either figure out where the substituent is, or you can figure out the number of carbons between the two functional groups. 1, 2, 3. So I've got 3 carbons between the functional groups, right? So I've got 1, 2, 3, 4 carbons there. 1, 2, 3, 4 carbons there. Those look like they have too many well, sorry. Let me write out the number of carbons so I don't confuse myself. Look like there were a few too many carbons. 1, 2, 3, 4 carbons between the functional groups, right? So I've got 1, 2, 3, 4. 1, 2, 3, 4. Those are looking good. 1, 2, 3. 1, 2, 3. A and B are out. Don't forget to count a carbon. Okay, now the question is, where is that methyl group? And so is the methyl group, well, it's 1 carbon away from the oxygen, right? So here's the oxygen, and my connectivity shows that I only have carbon 4 and carbon 3 right there. So 1 carbon away from the oxygen group is C. This methyl group, whoops, this methyl group is 2 carbons away from D. And so within, even though this question is complicated, within a couple minutes or 2 minutes, I can figure out that C is the right answer, and I think that's correct. Yeah. Good. Oh, we lost them. So in ring opening polymerization, you should be able to go back and forth between the monomer and polymer, and it's just a matter of counting carefully. It's a lot like when we did polyesters and polyamides and all the other types of polymers when we started the class. So you really need to look closely at the connectivity of the monomer and polymer and make sure that's represented in the repeat unit. Who doesn't understand in terms of the connectivity of the repeat unit why that's a polyester? Okay, it's okay if you don't. That was a long time ago, right? And so if you don't remember why this is a polyester, make sure that you're able to move those parentheses up and down the polymer backbone. And of course, we could write this a different way where the ester is together, right? And we just need to make sure the right number of carbons are in there. And so refreshing your memory on this is a good idea, because what's the other type of polymer? Well, we've got polyether, we've got polyester. What other types of polymers did we make using ring opening polymerization? Yes, polyamides, right? And so make sure you look that up in terms of those lactam monomers in the notes that you can make a polyamide from ring opening polymerization. Good. Questions on this? All right. So that will take a couple hours of your time this week in preparing for the exam, making sure you review all that old stuff, dienes, stereochemistry, and it gets serious with ring opening polymerization because there's a lot of things to remember in that. All right, we've done a lot with copolymers recently, so you should be well versed in this. You should be able to do the calculations mostly in the forward direction. You won't have to do them like the homework in the reverse direction, but knowing your way around what reactivity ratios mean. And I'm going to introduce a new type of question for you today. So you're really going to want to pay attention to this question in a second. And knowing how to interpret those plots is going to be really important. When you do have compositional drift, when you don't have compositional drift, when the reactivity ratios have a certain relationship to each other, what's happening? So to kick it all off, for reactivity ratios, what do reactivity ratios mean? What do they measure, or what do they signify? Go ahead. Homo over cross, always. Homo propagation over cross propagation. Which means when I ask you a question about a table coming up, you'll be able to tell me if the reactivity ratio is greater than 1, what reaction is favored. Homopropagation. So A active center reacting with A, or B reactive center reacting with monomer B. We don't have a subscript A or B on here, so it could be either one. If the reactivity ratio is less than 1, which reaction is favored? Cross propagation, which is A active center reacting with the other monomer, reacting with B, or B active center reacting with the other monomer, A. That's really important because that's the only way you'll be able to answer some of the questions on the exam. And I'll go through an example of that. All right. Small FA is the mole fraction of A in the monomer. You all know that. And you know that FB equals 1 minus FA. So that's why we, and capital FB equals 1 minus FA. That's why we don't have to solve both of the copolymer equations. If you know one, you know the other, because the mole fractions have to add up to 1, and we don't have any terpolymers or 3 monomer situations in this class. Capital FA is the mole fraction of A in the polymer, because polymers are great. That's why they get a capital letter. All right. If small FA equals big FA, what type of copolymer do you have? Random. That's the best answer. You don't really know the reactivity ratios because it could be an azeotropic polymerization. but you still get a random type situation because you're on the 45-degree line, capital FA, 1, small FA. Anything on this line is a random copolymer. Alternating is not a good answer, and block is not a good answer either, or blocky. If RA and RB approach 0 or are both 0, what type of polymer do you have? Go ahead. Alternating, good answer. It's not random, we just use that. It's not blocky. Blocky usually exists when the reactivity ratios, one's way above 1 and one's way below 1, and so it's not blocky either. Now, if the reactivity ratios are exactly 0, what reactions don't you have? If RA is 0, what does that mean? No homopropagation. So A active center will only add B. And then if RB is 0, B active center will only add A. That's how you get the alternating, because the active center of a certain monomer can't add itself. So you often don't have perfectly alternating copolymers. It might be one reactivity ratio is 0 and one is 0.05 or something like that. Bless you. That's pretty darn alternating. And so make sure that you have a little leeway in terms of blocky or mostly alternating. The one where it's random, it will be exactly on the 45-degree line because you don't have compositional drift. All right, if RA and RB are both less than 1 or both greater than 1, then there is or is not an azeotropic composition. There is. So it's special. You just basically have to remember that they both have to be less than 1 or both greater than 1, and what the shape of that plot looks like when it crosses a 45-degree line. Questions on that? Okay, so yeah, there's all the answers right there. So there's the potential for lots of plugging and chugging. On this exam, you're probably only going to have to plug and chug 2 or 3 problems because, you know, it's not an algebra quiz, but you need to make sure to know your way around these equations. And if you have hints about small FA and small FB and reactivity ratios, you're able to get the composition of the polymer. So what does an equimolar mixture of monomers mean?
When B is equal to 0.5.
Good answer. FA equals FB equals 0.5, right? Doesn't matter what the concentration is. If it's an equimolar mixture, that means the mole fractions are the same. And since we only have 2 components, has to be 0.5. So I don't necessarily need to tell you exactly what the mole fractions are. I could say the mole fraction of monomer A is 0.3. You automatically know what the monomer or what the mole fraction of monomer B is. It's 0.7. Or I could tell you they're equimolar mixture of the monomers, and you have to interpret those words in terms of what the math means. What is the azeotropic composition? What does this FA azeo mean? We haven't used this equation very much, but what does this mean? Why do we use this equation? It's the point where the plot crosses the 45-degree line. So you know if RA is less than 1 and RB is less than 1, you probably got something that looks like this, right? But the question is, where is this point? And this point is defined by the azeotrope. And so rather than plotting it all out and trying to figure out where that crossing point is for the 45-degree line, this small equation tells you exactly where it is. So if I give you a reactivity ratio of 5, RA and RB equals 3, and I ask you where is the azeotropic composition, you know exactly where it is depending on the reactivity ratios, right? You're solving for the monomer mole fraction, so you don't need that. You're solving for small FA. And then once you solve for small FA, you can plug it in and solve for capital FA, right? So you can get that, but you know that the azeotrope, they're the exact same, right? Because it's a random copolymer. And so just make sure you're able to recognize when you have an azeotropic polymerization based on the reactivity ratios and how to find that crossing point. That'll save you a lot of headache trying to figure out what the monomer mole fractions are, because you don't necessarily need it if you recognize that it's azeotropic polymerization. What's special about the azeotropic polymerization? Small FA is the same as capital FA, but what does that mean? When I say, oh, small FA is the same as capital FA, that's where it crosses a 45-degree line. What's special about that point? There's no compositional drift. That is a great answer. So anytime you're on the 45-degree line and you know that your polymer incorporation of the monomer is at the same mole fraction, you know that small FA is not changing. If you're off the 45-degree line, if your polymer is enriched in one monomer versus another monomer, that means you're going to be depleting that monomer in the monomer mixture. Small FA will change and you'll get compositional drift. So that's a lot of words. That's a lot of talking. Make sure you're able to walk that through on your own and then come and ask questions in office hours if you really don't get what that means. Yes.
So how do we know if we're exactly on the 45-degree line?
Yeah. So if you're on the 45-degree line, FA equals small FA equals capital FA, right? That's on the 45-degree line. Or you're at the azeotropic composition where small FA equals capital FA too. Yeah. That's the definition of the 45-degree line. Yes.
That's going to be all FAs or azeotropic or this one.
Yeah, there's only one azeotrope, right? So there's only one point in an azeotropic polymerization where small FA equals capital FA. And of course, if we have a random copolymerization where RA equals 1 and RB equals 1, every point is on the 45-degree line. Good questions. Let's see, what else? Yeah, okay. Copolymer composition drift. And so you know that as you go up in conversion, if you're not on the 45-degree line, you get copolymer compositional drift. Now, going to the homework, you had a couple of different curves, right? You had a couple of different curves that you plotted. This is the same plot we've looked at. But the question was, discuss compositional drift with all the situations. And of course, in an azeotropic polymerization, if you're at the 45-degree line, there's no compositional drift, just as we talked about. But what about comparing, say, this curve? And so this is RA equals 4 and RB equals 0.1, which is the long dash line. And we're going to compare it to RA. RA equals 2 and RB equals 0.5. So we're looking at this line right here versus this line right here. Which situation is compositional drift more severe? The upper one, the one that's further away from the 45-degree line. You see the reactivity ratios are further apart. These are it's the same situation, right? The polymer is always enriched in A because RA is greater than 1 and RB is less than 1. And these plots both tell you that the polymer is enriched in A because capital FA is always bigger than small FA. But in this situation where RA is 4 and RB is 0.1, the reactivity difference is greater, which means the compositional drift is going to be greater. You're farther away from the 45-degree line, whereas RA of 2 and RB of 0.5, even though the polymer is still enriched in A, you're going to get less compositional drift relatively because the reactivity is more similar between the two. So that was sort of built into the homework solution. I think I discussed it in the homework solution, but that's something to think about, is that compositional drift can be more or less severe depending on the situation. Questions or comments on this? All right, you can get out your clickers. Lots of clickers today, that's good. Okay, what are the possible values of reactivity ratios for this binary copolymer plot? So the way that you think about this during the exam is you take your equation sheet and put it up on the screen so you can figure out if this thing crosses the 45-degree line or not. It is hard for me to see just based on this plot. It, you know, kind of looks like there's an inflection point, right? But it's a little bit hard for me to see if this is azeotropic or not, or even if this thing is above or below the 45-degree line. And so make sure that you have a scrap piece of paper or something where you can put, you guys can't see that, but you can put your 45-degree line on there and decide what's going on. So if we do that, is this an azeotropic polymerization or not? Yes, turns out it is, because it goes both below and above the 45-degree line. If it gets really close to the 45-degree line, it's not an azeotropic polymerization unless it crosses, and you can see that. Okay, so the question is, which set of reactivity ratios here are an azeotropic polymerization? And I will likely not be mean to you and give you two choices, because remember, the azeotrope, when they're both greater than 1, the line goes down first and up second. When they're both less than 1, which is right there, the line goes up first and down second. I won't ask you to distinguish between the two because that's difficult depending on what's plotted. So which one is the azeotropic composite, or the azeotropic set of reactivity ratios in this list? RA of 1, RB of 1, no. One's greater, one's less, no. One's less, one's greater, no. Both greater than 1, that looks pretty good. That's our only choice. That's our best choice. We're not sure exactly if this should be like this. You know, I don't have my Excel sheet on the exam. I don't know, but this is the only azeotrope. So I won't ask you to distinguish between the two. And I think that's the right answer. Good. Yes.
You were just saying, like, how to determine whether it goes out first and up second or up and out first. So hypothetically, you know, RA is B and RB. If RA was 2 and RB was 4, would it still go out first and then up, or in that case, would it flip to go up first and then up?
No, it only goes out first and then up. So if they're both greater than 1, it's got this type of curvature. If they're both less than 1, it's got the other
So
type
it
of curvature.
doesn't matter which one's bigger between the two.
That's right. Doesn't matter which one's bigger. That moves azeotropic point up and down the 45-degree line. You don't have to know those details for the exam. You just need to know what an azeotrope is and why it's important. And you need to be able to calculate the azeotropic composition if I ask you, because that's important where no compositional drift occurs. Okay, you are all going to want to pay attention to these questions. And so if you have a friend who only listens to the video, tell them to fast forward to this part, because this is a key type of question that will help you study for the exam. All right. Which monomer has the highest reactivity towards the styrene active center? We could say the highest relative reactivity, right? Because we only know relative reactivities from the reactivity ratios. But the question is, which monomer is going to react with the styrene active center the most? So we have styrene, right? That's our active center. And it's going to add monomer M. So our monomer A is always styrene, right? So we have the reactivity ratios of A. And so we look on here and we see that, okay, styrene it really doesn't want to react with itself because none of the reactivity ratios are above 1, or none of the RAs are above 1. And let's see, the highest value, the lowest value, it's got to be one of those two. Styrene is really going to want to react with what monomer? Which reactivity ratio for the styrene active center, so it has to be Ra. We can forget about Rb because that's the active center of monomer B, right? Its reactivity. So where is cross propagation the most favored? Go ahead.
It's maleic anhydride
Maleic anhydride. Why is it maleic anhydride?
because that value is the smallest and total propagation of the cross propagation.
That-
It's the smallest value.
That's right. So Ra is going to be styrene reacting with styrene over styrene reacting with B. And so the smaller the value is, the more that you're going to have styrene active center reacting with monomer B. And so we're looking for the smallest value of Ra. That's really interesting. And I think the answer is maleic anhydride. There we go. So that's tricky, right? Because you need to remember what the reactivity ratio means in terms of your 4 fundamental reactions. And then you need to really ignore Rb, right? Because we ask about the styrene active center. And the only numbers up here that comment on the reaction of the styrene active center is Ra. And so we're looking for cross propagation, right? Yes.
So they ask for the like maleic anhydride active center when we look at RB.
Yeah. So if the question was, what is the maleic anhydride active center really reactive with? Or let's say, does the maleic anhydride active center want to react with itself or with styrene? That's the only information we have, right? Because we only have one maleic anhydride in here. So what's favored? Homopropagation of maleic anhydride or cross propagation of maleic anhydride? What would you say? Cross, because the reactivity ratio Rb is 0, which means maleic anhydride doesn't react with itself at all. Homopropagation is 0, and so it's only cross propagation. So you're right. Yeah. Walk through that table and decide, okay, homopropagation versus cross propagation. And what can you figure out from the reactivity ratios? All right, everyone's got their answers in. Here is another question to warm you up on that. Which is more favorable? Reaction of styrene active center with another styrene monomer or with a butadiene monomer? So we have polymer, styrene, active center. Is this going to want to react with styrene or butadiene? And so where do we look to find that information? What reactivity ratio do we care about for this situation? Ra in the styrene butadiene column, right? Because the other monomers would be another reactivity ratio. So what does an Ra of less than 1 mean? What's favored? Cross propagation, right? B. So it's tricky. You need to figure out what the active center is. You need to figure out what reactions I'm talking about. What's homopropagation, what's cross propagation, then what does the number mean? This is a different type of question that you should study and think about in preparation for the exam, because this is a really easy way to ask you whether you really know what reactivity ratios mean in terms of our 4 fundamental cross propagation and homopropagation reactions for A and B active centers. This is the hardest type of question on the exam. I promise you that. Oh, we're losing people. Make sure you ring it. I think butadiene's the right answer. Good. There we go. Any questions or comments on that? Yes.
So if we're given RB less than 1, do we still assume that cross propagation is going to be favorable? And like, we're not going to get much information about it.
That's right. So if RB, let's take this example right here. Let's say we're talking about methyl methacrylate active center. So let's copy this over, see if I can copy that. Let's insert a new slide. Look at that. Paste that back in. Okay, let's talk about methyl methacrylate. And we need to get the right compound, right? Because we have methyl acrylate on there and methyl methacrylate active center. So methyl methacrylate active center is only going to be this data right here, right? There's no other methyl methacrylate active centers in this whole table. There's a lot of different styrene active centers, right? Because styrene is always a monomer. But this is the only entry in the table that talks about the methyl methacrylate active center. RB is the only number that talks about the methyl methacrylate active center. So is cross propagation favored for methyl methacrylate or homopropagation? Cross. So methyl methacrylate active center prefers to add styrene. It's as simple as that. If you can find the right information and understand exactly what it means, right? Because we don't analyze, I mean, you can conceivably get the right qualitative answer if you see that 0.52, but that's discussing the styrene active center and its reactions. And so I could ask you, in this pair, I've got styrene active centers and I have methyl methacrylate active centers. What prefers to add what? And you'd have to compare the reactivity ratios. So because the styrene, because RA is slightly higher than RB, there's a slight preference for styrene to do less propagation, right? Less cross propagation. Little bit more homopropagation, but they're pretty close to one another. So we can compare qualitatively the two numbers. Of course, it's easy when one's above one and one's less than one. In the case of, say, styrene and butadiene, butadiene prefers to add itself. A butadiene active center prefers to add butadiene, and a styrene active center prefers to add butadiene as well. So is this polymer enriched in butadiene or enriched in styrene? Polymer is enriched in butadiene. Right, we can look at the reactivity ratios and say, yeah, of course, the reactivity ratio of butadiene is greater than 1, styrene is less than 1. But now we know why, because the homo and cross propagation reactions. All right, do I have any more? Okay, last one. Which is more favorable? Reaction of the methyl acrylate active center. Which number on this table talks about the methyl acrylate active center? There's only one number that discusses this. 0.18. This number right there. That's it. With another methyl acrylate monomer or with the styrene monomer. So I've got styrene in there. So does it prefer methyl acrylate or does it prefer styrene? Styrene. Boom. Hey, ring in. I think that is all the questions. Well, there's a couple more. Oh, I forgot. Remember your conformational models. This is the last thing I want to make sure you have. Thanks for that. I just summarized them here. We just talked about this, and so make sure that you review this. But since we just finished this up on Friday, this should be a lot fresher than the other stuff. I really wanted to go over those reactivity ratio questions. But remember all the different ways to describe a chain. Don't forget office hours, make an appointment, send me an email, and find a good place to take the exam on Wednesday. Thank you very much.